Okay.
I'm gonna let you go first, Hui. Just because I don't know. I would hope the first page looks like the 2021 exam instead of our terrible thing.
Yeah, wait, hold on.
Oh, I just realized there wasn't any multiple choice on ours.
No, it's not this. It's not this. Why is it? Okay, whatever. I just hope this works. Share screen. Hello. Oh,
There we go.
what just happened?
Is it small for you or is it the whole
Oh,
screen
can you
for
see?
you?
Can you see it now?
Yes.
Okay. Wait, let me check OBS. Oh shit. Oh. Okay. I got it. I got it. So I'm like screen recording and doing. Okay. I think we can go back to naming because naming is more like self-explanatory. You guys have been doing it, so it shouldn't be that bad. Okay. So these are mechanisms. So first, you should look at these steps.
Oh, wait, Hui. I don't see that screen. I see the Orgo 1 team screen. Does everybody else see that, or is that just me?
Nah, we see it too.
Oh, okay.
See. Oh. Okay, see it now?
There we go.
Yeah, okay.
Yes, see it now.
Okay, so for this third test, she also mixes in like the SN1, E1, E2, whatever. So this first step is actually E2. And how do we know this, right? Because we have an Na, so that means this is a strong because it has a charge, right? And then if we look at this this base part, looks like this, right? And this is really bulky. So if it's a strong bulky base, we know that it's gonna be E2. Okay. And then remember for E2, we have to have a hydrogen that is trans to the Br. So this first step is going to be E2. We're going to use this base, attack this hydrogen. The bond for the hydrogen is going to go down here. And then this leaving group is going to leave. This is just a regular E2 mechanism. Okay? So what's going to happen is that here, the Br is going to leave. So we form an alkene, okay? Using the E2, we attack this hydrogen, move the bond for the hydrogen down here, and this leaving group is going to leave at the same time. Okay, and that we're creating an alkene. And the second part of this reaction is just an alkene reaction. So you guys should also know this mechanism. It's going to be this double bond attacking the hydrogen, bond going to the Cl, okay? And what that creates is it's going to create a carbocation. Since carbocation is going to be more stable here, so we're going to put it, because remember, if we put the carbocation here, it would be on a secondary carbon, which is not as stable. Over here it's tertiary, which is more stable. Okay, so now we have this carbocation, and now we have this Cl minus, right? Because when you attack the H off the Cl, this bond is going to move to Cl, creating a negative charge. And then what's going to happen is that Cl is going to attack the carbocation. Okay. I'm going to get this. And remember, it says no optical activity. That means is that there is no chiral center, and right here, it's not chiral, so that's correct. And again, remember that this HCl mechanism is going to be added mark because if you look at the mechanism, right, we're creating a carbocation, and carbocations are more stable when there's more substituents, right? And remember that mark means that this is going to be added to the more substituted carbon. So the reason why it's being added to the more substituted carbon is because the carbocation is formed on the more substituted carbon. That's why it's added. So any questions on this one? This is just an example of how, like, kind of old stuff like the E2 and, well, you form the alkene, right? And then the new alkene reactions are like being put together. So any questions on that? Okay, this one, same thing. So notice we have the HCl and we have the alkene. So what's gonna happen is that the alkene is gonna attack this here. If you guys notice, like a lot of the steps, it starts off with the alkene attacking something else. So if you get lost, like just remember that the alkene can attack stuff, and then that will like open up your options. So what's gonna happen is that the alkene is gonna attack the hydrogen, creating a carbocation. Remember, carbocation is going to be put. We have two options where to put the carbocation, here or here, and we're obviously going to put it here, right? Because it's tertiary, so that means it's more stable. And if you're wondering, like, when you attack the hydrogen is going here to the other carbon. So one of the carbons is going to have the carbocation, and the other one's going to have the hydrogen. Okay. So now we're going to get the Cl minus. We're going to have it attack right there. Okay. And now we have this for the first step. It's the end of the first step. Okay. And now we have here, we have a strong nucleophile, because remember it's Na, so it's going to be strong. We have SH. So this is basically an SH ion. And it's an acetone, which is a polar aprotic solvent. So this means it's going to be SN2 reaction. So if we're looking at our product right here, we have two leaving groups, so one here and one here. So for SN2 reaction, right, we're going to favor a primary carbon versus a tertiary carbon. So we're going to actually attack this carbon right here. Even though we added the Cl over here, it doesn't. We're still going to look at this as like a whole product, right? It doesn't matter that I just added this, that I'm going to use it for SN2, right? Because this is the better leaving group for SN2, so I'm going to use this one. So what's going to happen is you're going to have the SH. It's going to attack. Do okay. And now we're going to do this one. So if we look here, this is something we've seen before, right? This is going to be SN1E1 because of it's polar protic, and it doesn't have like a Na or like a K, right? So it's gonna be a weak nucleophile / base. Okay, and then we can eliminate SN1 right off the bat, right? Because if you look at the final product, we're not substituting this group onto it. That means it has to be doing E1 reaction. Okay. So for E1, the first step is leaving group leaves, right? Okay, so we have this step now. So how can I get this double bond to look like this? So what it looks like is that this double bond kind of moved over here through resonance. So it might, like with these types of problems, it might be hard to see at first, but you're just gonna have to get used to like kind of thinking like, where can I move stuff? And if you think about it, right, if I move this double bond here, we're gonna put we can move around the carbocation, and maybe we can use E1 to put the double bond where we want it to be. So first, we're just gonna do resonance. One here. Okay. So now we have the carbocation here. If we form a double bond here, that's not the final product we want, right? So how can we move this carbocation to make a double bond here? Well, we can do a hydride shift. So we put the hydrogen here. Now we're putting the carbocation in here. Okay. So now with the carbocation where we want to, right? Because now we can use this hydrogen right here as an E1 reaction. So we use the OH from the reagent. Boom, this down. Then we're gonna get the final product. Okay.
Before you move on to the next one, Hui, at some point, some people wanted you to go back. I'm not sure what spot they meant to. You guys in the chat who wanted Hui to go back and say something again, what part did you mean? Was it on this question, or did I miss it and it was on the previous question? I don't see anyone saying anything again. Okay. 2B? Okay.
Okay, 2B.
What did you want re-explained on the previous question? Wait, do you just want to give a run through of this one just real quick one more time?
Yeah, okay. So the first step is going to be one of the newer reactions you learned, right? It's going to be a addition of the HCl to alkene. So we're just going to attack the hydrogen, and the product is going to be this. So here, let me erase this. So this is the product of the first step, right? What we did is we basically just turned this alkene to this Cl and the hydrogen over here. We just replaced the alkene with a hydrogen and a chlorine. Okay, so now for the second step, it's an SN2 reaction because we have a strong base, and also if you look in the formula, you see there's a sulfur, right? So that means we clearly added something, so it's not going to be E2, because if it wanted E2, it would not have sulfur in the instructions, right? So now we know that it's an SN2 reaction, and when we look at this product that we got after the first step, we notice we have two leaving groups, and from here we got to pick the one that's more suited for SN2, right? So this one is kind of inside the middle. It's going to be hard for the sulfur to attack, but this chlorine out here is it's on a primary, so it's easy to attack from the back side. So we're going to use this attack here. Chlorine's going to leave, and then we're going to get this product. And then what I was saying about so even though this is the chlorine we added with the first reaction, right? And this chlorine was already in the product. It doesn't matter that I added this one later. It doesn't mean that I'm going to use it for the SN2 reaction, right? When you look at this product, you see that this one is better for SN2, the one that was already on there, and that's just the one you're going to use. Just because you added a group doesn't mean you're immediately going to use it for the next step. That's what I'm trying to say. So any further questions about this one? right? This one.
Hui, out of curiosity, do you know how to like invite someone to a meeting?
Invite. I think they just click on the link, right? Here.
I know, but it's not working for someone.
Oh.
I'm just not sure if you would have to do it as the host. I don't see an invite button somewhere.
I don't see. What is this? Yeah, I don't know. Okay. It's recording. Alright. I have no idea. But let's just move on. Sorry, I'm not very good at Teams. Okay, so
I mean, if anybody else knows, yeah.
okay, this one is just you're gonna see this one a lot, but so it's really important to know this mechanism and also like which one is trans, which one is cis. So what happens is that you have the two BRs here, right? It's gonna do this weird like cycle attack thing. Remember, the double bond is like the alkene reactions. It like likes to attack stuff because it's electron rich. So usually the double bond is attacking stuff, and then the BR is attacking back, and it makes this weird tent, right? So it makes the tent. I'm gonna draw my wedges like without coloring it in because it makes it hard to it, like erases it for some reason. So it's gonna look like this. Sorry. Okay, it's gonna be like this BR tent. I usually like do it with wedges. I just keep it consistent. And also remember it has the positive charge. Don't forget that. Okay, so then what's gonna happen? Because the reason why it's trans is that H2O is gonna attack this center right here, and it's gonna invert stereochemistry. So what happened is that it's gonna force this group to become from dashes into a wedge. So we got BR wedge. And remember, like the BR is going to lose its positive charge because it's gaining like this bond right here. Okay, and then we're going to have methyl is now going to be on a wedge. So this methyl right here that was previously on a dash is now going to be on a wedge because the H2O inverted it. And now the H2O is going to be right here. But it's going to be in the weird like positive form. And when you see this positive form, you guys know what to do. You just use a water or anything just to get an H off and make it into a OH. Okay. Another thing to note is that this H2O will always attack the more substituted carbon. So this reaction is known as MARC. MARC. And then also notice how the final product, the OH and the BR, these are the groups you added, right? They're going to be trans to each other. And then also another thing is that you see how I drew the BR on a wedge and an OH on a dash here? Whenever she asks you to draw all the products for this reaction, you also have to draw the other form, which would be so it would just be like switched. So here it would be on a wedge, dash, dash, wedge, but make sure they're trans to each other when you redraw them. See if they draw both.
Perfect. I think I'm gonna let you try and figure out how to maybe resend that link to the
Yeah.
person who's having difficulty getting in. I'll take over, and I think I'm gonna do mechanisms again, and then we will move on to the next section. So let me just share my screen really quick. All right, tell me when you guys see it.
Chat.
All right, can we see the screen? All good?
Yeah.
Okay, perfect. Thank you. All right, so moving on with mechanisms, because all the mechanisms are very important. The nice thing is, if you were at my alkyne session, you don't really need to know a lot of the alkyne mechanisms. A lot of the mechanisms are going to revolve either around alkenes or just general type mechanisms similar to the E1, E2, SN1, SN2 reactions. So when we look at this mechanism, we have an alcohol group, which is not a good leaving group of in itself. And we also have essentially H3O plus, acidic water. And we want to make 2,3-dimethyl pent-2-ene. So I always start by just drawing out what the product's going to be. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Perfect. 2, 3. 1, 2, 3. 1, 2. Pent-2-ene. All right. And I'm actually going to draw it the other way around just because it'll make more sense with the mechanism. Perfect. Okay, so we know that we're doing a dehydration reaction. We're going to try to remove this alcohol group using our acidic water to make an E2 mechanism, or an E1 mechanism in this case, to form an alkene. So to start off, we need to make water a good leaving group. So we have H plus in solution. And your alcohol group has lone pair electrons. So it's going to use its lone pair electrons to acquire this hydrogen ion in solution. So what this ends up with first is you have OH2. So essentially a water molecule that's positively charged on your carbon. And so while an alcohol group in and of itself is not a good leaving group, when you protonated it to make this positively charged OH2, this is a good leaving group. So this can leave all on its own, which it will do to make the next intermediate a carbocation. And so if we remember, a carbocation always pretty much wants to be in its most stable form. And if we just dehydrated this and did our E1 mechanism on either the hydrogens on this side or the hydrogens on this side, we would not end up with the product that we want here. We want the alkene to be on this carbon. So what that means is we need to do some sort of shift. So we have a hydrogen on this carbon that can do a hydride shift to make a more stable carbocation. So once we've done our hydride shift, I'm going to remove the stereochemistry here because it's no longer an sp3 carbon. We end up with a positive charge on this carbon. So we have several options now where we could do our E1 mechanism, our dehydration, to make our alkene. We could either do it on the hydrogens on this side, but that wouldn't get us the product that we want. We could do it on the hydrogens at the end of this methyl group, but that also wouldn't give us the product that we want. The only one that would give us the product that we want is the hydrogen that's on this other side. So water, which is a pretty good base, even though it's weak, is going to come in as a base and remove this hydrogen to fix our charge. So it's going to remove the hydrogen, and the lone pair that once was attached to the hydrogen is going to come down and form that double bond, fixing that carbocation charge. And so what you end up with is 2,3-dimethyl pent-2-ene. Perfect. That's exactly what we wanted. Matched exactly. Any questions on that one? That one's just a simple dehydration reaction. And it actually helps a lot because an alcohol isn't a good leaving group, and even on into organic 2, sometimes you need to make it a good leaving group. Okay. So moving on to this one, what they want. So we have KOH. I know from experience, I'm going to want to label this. So I know I have a strong nucleophile or base to work with. And so we want a molecule with the molecular formula C8H14. And specifically, we want the Say-Zephs product. So some specific terminology here. The Say-Zephs product is going to be the more stable product, which ends up being any kind of internal alkene. Now, they also could have asked us for the Hoffman product. Now, what this means is they would be asking for the less stable product. They're both stable, but one's going to be more stable than the other, and that ends up being a terminal alkene generally. So just some terminology things there. So let's go ahead and count all of our carbons on here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 carbons on here, so we're not doing anything with our carbon count. And since they're asking for the Say-Zephs product, we know that they're going to want an alkene. So KOH could be doing acting as either a strong nucleophile or a strong base. But because they're asking for an alkene product, an elimination product, we know it's going to be acting as a strong base rather than a strong nucleophile in this case. So this ends up being a pretty easy mechanism. Because it's a strong base and we don't actually have any solvent information to work with, we know that we can do an E2 mechanism on it. Actually, I'm going to use what they started with. So if we want the Say-Zephs product, we want an internal alkene, we could either use a hydrogen on either carbon beside it. Now let's check where our hydrogens are because they need to be trans if we're going to be doing an E2 reaction. Okay, the hydrogen on the top carbon is cis with the bromine, so we can't use that one. The hydrogen on the bottom carbon, however, is trans, so we can use that one. So this time our hydroxide ion, which is negatively charged, is going to act as our base, and it's going to pluck off this hydrogen, moving the electrons down and kicking off the bromine, all in one singular step. And so what we end up with as our product, I'm going to try to draw my pentagon, my cyclopentane, is this. And so, for example, with this question, if she had asked for the Hoffman product, you would have used a hydrogen over here to give you a terminal alkene. Now, I knew I had to look at either the top or the bottom because I wanted an internal alkene, which I would not get if I used this methyl group's hydrogens. Any questions on that one? That one was just a quick one step. Okay. All right, this is actually my favorite type of mechanism that you're going to see. Now, what acetylene is, if you remember, again, this is another terminology thing, is it is this sad child. One hydrogen on either end of it. Pretty much a 2-carbon terminal alkyne, not alkene. And so what we want is an alcohol containing final product. So let's look at the reactants we're given. So we have NaNH2. I know those are charged. I'm just going to go ahead and write it so I don't forget. We have an aldehyde. And we have acidic water. So what does NaNH2 do? That's going to form us that terminal carbanion on an alkyne. So let's go ahead and see what step 1 does. Forms for our product. We're just going to do a little trial and error. We're going to take a hydrogen, doesn't matter off which end. They're both a terminal end. We're going to end up with, I'm going to draw out the carbons just so I don't forget. We're going to end up with that carb anion, which acts as a really good nucleophile. So now let's move on to step 2 and see what happens with step 2. So using the product that we formed in step 1, it can go on to act as a nucleophile and move these electrons, because remember, electrons can kind of act like a good leaving group. And so it's going to force these electrons back up into the oxygen, which can take it. Oxygen's relatively electronegative, even if it's not the happiest in that state. So now, you just need to remember that we attached this carbon on. I'm going to put it up here because that's where I drew it. You just have to be careful that you're attaching it in the right place. We still have that triple bond to the other carbon and the hydrogen on top. So that's all been added nucleophilically. And this does still have a hydrogen. I just didn't draw it right away. And now you can see it's very easy to get an alcohol-containing final product. We have acidic water in solution, which has H+, and a negative oxygen, which acts as a really good base. I put H-. And it can very easily just pick up a proton, ending up with an alcohol containing final product. Any questions on that mechanism? For this kind of question, it's really important for you to count your carbons. I think I might have added a carbon somewhere. 1, 2, 3, 1, 2. I did. As I said, it's very important. Oh no, I can't just redraw it. It's very important to count your carbons here. I added one very easily. I only need 3 carbons. Perfect. There we go. That's correct. I have a bad habit of doing that. So at the end, I always like to go back and count and make sure I have the right amount of carbons. Okay, if there's no questions on that one, I'll be moving on to this one. Again, as you can see on this test, she likes to do a lot of terminology things. So what exactly is the halohydrin product? That's going to be the product that has 1 halogen, so in this case a chlorine, and 1 alcohol group. It's in the name pretty much. Halogen, chlorine, hydrogen, hydrin, like hydrogen, alcohol group. Okay. That doesn't change a whole lot about how we're going to go about this mechanism, but it does change just a little bit about which step we end up taking to get the final product. So first things first, we have our 2 chlorines, and this alkene is going to act a bit nucleophilic. It's going to grab one of the chlorines, and because the chlorine is a bigger molecule than a hydrogen, it's going to fight over who gets to have the chlorine. Neither of the alkene carbons are going to be able to decide exactly who gets the chlorine. So we're going to pitch this tent structure. Okay. Once we've pitched this tent structure, then, so we want the halohydrin product. I'm always going to say that wrong. We have multiple options. We could have the chlorine that we have left over come in and attack, but that would just give us a dichloro product. So that's not what we want to happen. Or we have water in solution, so we could have water come in and attack, and it's always going to attack the more substituted carbon. So it's going to attack the carbon up above. And that would give us a halohydrin product. So that's going to be the next step we're going to want to take. having water attack the more substituted carbon. So when water attacks the more substituted carbon, if we add a bond there, oops, carbon's got 5 bonds, so now we have to kick something out. And the easiest thing to kick out is this pitch tent to chlorine. So we're going to give those electrons back to chlorine. So what we end up with is, now we still have the chlorine on a wedge down here, and we had to attack from the back because of that tent structure. So we know that water, or the water that we've added, is going to be trans to that chlorine. We haven't lost any hydrogens yet on that water, so it's still positively charged. And then we can't forget to add in the methyl group that was still there. It's going to be a little bit ugly. And then the very, very last step is to just have that hydrogen be removed. I'm just going to go ahead and use that chlorine that we produced in an earlier step that has a negative charge. It kind of wants a buddy. And so we are going to grab just any hydrogen and return those electrons to oxygen. And so what we end up with, still trans, an alcohol group, and a chlorine. And then lastly, that methyl group that was still there. All right, any questions on that mechanism before I continue on to just reactions? Trying to make that a little prettier. All right, if there aren't any questions, I'm going to just continue right along. All right, so this one we don't have to actually draw the mechanism. Thank goodness, because a lot of these we don't know how to draw the mechanism for, but we do need to draw the final product. Okay, well, let's look at what we have here. We have a chlorine on an alkene, a good leaving group, and this whole sucker right here can be abbreviated as OTOS. It's an O-tosylate. If we remember, it's also a good leaving group. Now what reactants do we have? We have excess KOH and high heat. Now, if we remember, looking back at our reaction summary, this is the conditions that we would use to form an alkyne. And so that's very important. So we know that we're going to use this chlorine good leaving group in order to form an alkyne here. But wait a minute, KOH is a base. And since we're already doing an elimination reaction to form an alkyne, we could very easily do an elimination reaction on this OTOS group. So actually, we're going to make 2 elimination reactions happen. So let me count my carbons 1 second. 1, 2, 3, 4, 5. We have 5 carbons. We know we're going to make an alkyne, so let's go ahead and draw that. Starts on the second carbon. So 1, 2, 3. And we know we're going to make an alkene off of wherever this good leaving group left. So on the 4th and 5th carbon. 4, 5. Ooh, that looks ugly. 1 minute. I'll just draw it down. Perfect. So that's the only product for this. Don't forget to write your excess product. We know we have OTOS minus, or you could call it K-OTOS because it's paired with a positive potassium. My handwriting gets worse and worse. She does like it when you have the tosylate product because that is a big product hanging around in solution, even though it's just a byproduct, and this is the main organic product that you will be making. All right, moving on to 4B, we've just seen this reaction. We just did a mechanism for it. So we have Br2 and H2O. So we could either form the halohydrin product or we could form a dibromide product. All right, let me show. Let's do the dibromide product first, just because that's easier. So we know we're adding 2-bromine trans. And now we just need to add the rest of it. So we still have a deuterium on the top carbon. We do need to show that. And we still have a methyl group on the bottom carbon. And we also have the enantiomer of this. I'm just going to write. Hui, if you remember, she does take the and enantiomer on the test, right? I'm pretty sure she does.
I'm pretty sure she does. I would do that too because it's a lot easier.
Yeah. Okay, now let's do the halohydrin product, which we've just shown before. Now remember, the water part, or what's going to become the alcohol part, is always going to sub the more substituted alkene carbon. Deuterium is pretty much just a hydrogen, so that one's probably not going to be the more substituted carbon. But down here, we have a separate methyl group. So we essentially have a double substituted carbon on the bottom and only a single substituted carbon on the top. So this bottom carbon is where we're going to be adding our alcohol portion. So let's just go ahead. I didn't draw my bromine in. There we go. Or maybe I erased it. Let's go ahead and draw the halohydrin product. Alcohol on the bottom, the bromine on the top, and we still need to show that deuterium and that methyl group. Perfect. And once again, it could have been the alcohol on a wedge and the bromine, or alcohol on a dash and the bromine on a wedge. I just didn't draw that product, but I'm just going to write and enantiomer to save time. Perfect. All right. Now let's look at this one. So once again, let's just look at the substrate first. So we've got an alkene. Okay, a lot of things we could do with that. Now what's going on here? So what's going on over here is she just has it written in abbreviated form. So I'm going to draw out what it looks like down here. Because there's only one hydrogen on the end, we know that it's a terminal alkyne. Okay, good to know. And we know that we have a 3-carbon substituent coming off that propene ring. Perfect. Now let's look at what we have here. Okay, CaBH, tetrahydrofuran, hydrogen peroxide, as well as sodium hydroxide. And we have both of these in excess. So we know that this is a reactant we've seen with both alkenes and with alkynes. When we see it with alkenes, we know it's going to add H and OH to an alcohol group, but it's going to be adding it anti-Markovnikov. Ooh. I can't spell it. That's why you just say anti-Mark. And is also going to be adding it cis. When we've seen it with an alkyne, we know we're going to be undergoing tautomerization, and it's also going to be anti-Markovnikov. Perfect. Hard word to spell. I'm going to scoot this up here just so I have a little space. All right, so we have an alkene and an alkyne in this problem. So let's go ahead and look at the alkene portion first. So we're going to add H and OH, anti-Markovnikov. So that means we're going to want to add the H where there's less hydrogen. Which part of the alkene has less hydrogen? The part substituted with the methyl. So this is where we're going to add our hydrogen. I'm just going to draw it on here. This isn't the product. And we're going to add our alcohol to the bottom portion, anti-Markovnikov. When we have an alkyne and we want to tautomerize it, anti-Markovnikov, that means I'm going to draw the alcohol product first. We're going to add the OH to the less substituted carbon. Let me go ahead and get rid of one of these to make it look like an alkene. So this is the enol portion before we finished our tautomerization. And essentially how I always draw it, finishing my tautomerization just to remind myself what I should do. This isn't the mechanism. I just scoot the double bond up there to remind myself I need to make that a ketone, even though it starts as an enol. So let's go ahead and draw the product. Start off with my cyclopentane ring. It's no longer an alkene. I'm just going to draw this as a wedge just for the heck of it. And then we also have the hydrogen. You'll see why I'm drawing it out in just a second. You don't have to draw it out. But since we're adding anti-Markovnikov cis, it means that this one down here, the alcohol group, also needs to be on a dash to make it match up cis with the hydrogen we added as well. Now let's go out to the other one. 1, 2, 3 carbons. And let's add our aldehyde on the end. Pretty simple. I did not think it was simple. And once again, on this problem, I always have to make sure I count how many carbons are coming out, especially when you're changing it up. It's easy to lose or add carbons. On my test, I lost a carbon. I had 2 carbons instead of 3. And it was like, well, where did that other carbon go? It disappeared. Any questions on this one? So whenever you see anything like 2 moles, or it might just say excess, that doesn't always mean that the reaction's gonna occur multiple times. But if you don't see it, it's usually a good indicator that the reaction's only going to occur once, as opposed to multiple times. Because if you have only a 1-to-1 ratio of substrate and reactants, you're gonna use all that substrate with the reactant, and there's not going to be any to do the reaction again. All right, so this is actually the opposite reaction of the dehydration that we saw earlier. This is a hydration reaction. So anytime I see a strong acid like this, I know that I'm going to add H as well as an alcohol, and I'm going to add it Markovnikov. Perfect. All right, well, let's look at our alkene. It's internal. Both of the sides are equally substituted. So that Markovnikov doesn't really make a difference. We could add it to this side, or we could add it to this side. And let's go ahead and draw out all of our carbocation intermediates. Because on this problem, we add the hydrogen first. It just grabs a hydrogen off of the sulfuric acid, leaving a carbocation on the other side of that alkene. Okay, so the first possibility, I could have my carbocation on this carbon. So I took the hydrogen and I subbed it in on this carbon here. My second my second carbocation possibility would be that I put the hydrogen on this carbon, and so I make my carbocation here. Try not to lose any carbons here. Okay. Well, let's look at these. Are there any possible rearrangements on these carbocations? Down here, the carbon to the left and the right, I'd make the same priority, same substituted carbocation. So nothing's going to happen there. This top one, however, we can very easily do a methyl shift to make a more stable carbocation. Okay. Try not to lose any carbons here. So there we've made all of our possible carbocations. And so really now it's as easy as saying, well, where are all my carbocations? I'm just going to stick an OH on each one of them. So I'm just going to erase where I've got my carbocation and just put my OH on there. Yeah, perfect. Going to do that for all of them. Going to go ahead and erase my methyl shift. And then the last one. Okay, and because we used a carbocation intermediate, we don't know whether these added on a wedge or a dash. They could have added on either. So I'm just going to put that little star indicating that that alcohol group and that hydrogen on that carbon could be on a wedge or a dash. And on the carbon that we did a methyl shift on, we actually need to add 2 because we don't know when this methyl group was moved over to where the carbocation initially was. We don't know if it became a wedge or if it became a dash. So we really have 1, 2, 3, 4, 2 to the 4th power, 16 products here. And so it's a lot easier to draw it like this as opposed to this. Maybe it's 4 squared. Yeah, 16. Did it right. All right, moving on. Okay, we see warm potassium permanganate and acidic water. This automatically means cleavage. So what I'm going to do is I'm just going to draw a cleaving line through both my alkene and my alkyne. Remember, it cleaves both. It cleaves them ever so slightly differently, though. So, okay, we have a terminal alkyne, which has 1 carbon on one side, and then a carbon attached to a carbon on another side. When we see a strong oxidizing agent like KMnO4, this 1 carbon ends up oxidizing all the way to CO2. For the other side, which is still attached to a carbon, what we end up with is a carboxylic acid, so a COOH. Now let's look at the alkene. Okay, we have a disubstituted alkene, so that means we're going to end up with a ketone. Not ketone, ketone. And on the other side, we only have a monosubstituted alkene. So again, we're going to go all the way to a carboxylic acid, COOH. All right, now let's just draw all of our carbon products. I'm going to go left to right. So we have a 2-carbon carboxylic acid. I drew 3. It's okay. Two-carbon carboxylic acid, so that's the leftmost portion. In the middle, we have 1, 2, 3, 4, 5, 6, a 6-carbon element. 1, 2, 3, 4, 5, 6, and let's see, 1, 2, 3. On that 3rd carbon, we're going to have a ketone where we cleave the alkene. 4, 5, 6. On the 6th carbon, we're going to have a carboxylic acid where we cleave the alkyne. Perfect. And just to finish off, I like to count all my carbons just to make sure I got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. We got all 9. We did our cleavage correctly. Perfect. All right. Here's another terminology thing that we should probably know. So MCBPA. This is a peroxy acid. So what does that mean? We're forming an epoxide. And so if we just had MCBPA, our final product would be the epoxide. However, we also have acidic water. So that means we're going to break the epoxide ring, ending up adding. So our overall, we're going to add 2 OHs trans. That's what this mechanism produces. So let's go ahead and do that. We didn't touch this substituent over here on the left-hand side, so I'm just going to leave it as it was. I'm just going to add my 2 alcohols. I'm going to start with the one on the wedge down here, the one on a dash, and then the ethyl substituent still has to be in there. Okay, in this case, we could not just say and enantiomer. Why? Because it would switch this substituent on the left-hand side from a wedge to a dash, and that would not be the correct product. So we do actually have to draw out the full second product. That's where you have to be careful of saying and enantiomer, because it doesn't always work when you have other substituents that aren't affected by the reaction that preserve their stereochemistry. We're going to add our first alcohol on the dash up there, and now our bottom one is going to be on a wedge. And then the ethyl substituent is now on a wedge. And then another thing that it's good to write is the remainder of the peroxy acid. R, you can just substitute in for R. You just need to know that it's become a carboxylic acid. R just means any group. I don't exactly know what MCPBA looks like, but I do know that it ends up with RCOOH as the final product, as what's left of the peroxy acid. Okay. Man, this goes on forever. Wait, was it really this long on the test?
I don't remember. I don't remember taking this test.
All right, moving on. We have 2 alkenes. But what do we have for our reactants? We have NaNH2 and CH3I. Now, what does NaNH2 do? It takes a terminal alkyne and makes it into a carb anion. Do we have any terminal alkynes? No, we don't have any terminal alkynes, so we can't do anything with step 1. If we look at step 2, we have a leaving group, nothing that's really nucleophilic or basic, so there's nothing that we can do. This is no reaction. And it's because NaNH2 is used to make a terminal alkyne into a carbanion. We don't have a terminal alkyne on this substrate. We have a terminal alkene. If anything were to react, it would be reactants 1 and 2 with each other, but you wouldn't have to write that. So there is no reaction here. You just have to be careful with that. That's where it's good to know your reactions and what they're specific for. Okay, let's look at the next one. We have an alkene and we have an alkyne. In our reactants, we have H2 and Lindlar's catalyst. Well, what does that do? It makes a cis alkene from an alkyne. What else do we have? Excess CH, and KOH. So we have excess, so that means we could do it more than once. We'll see what happens after step 1. And this is that reaction that forms, it's almost an epoxide, but instead of an oxygen at the top of the ring, it's got that carbon with 2 halogens, that geminal dihalide ring. Perfect. Okay. Now, if we make what happens from step 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, we have 9 carbons. I'm going to start with my cis alkene that we form from our alkyne. Three, 4, 5. Perfect. Okay. Well, now we can easily see that we're going to be adding with this excess, this both here and here. We have 2 options of where it could go. So to give me a little more space, I'm going to erase this. Just put it up here. So we just have to be careful. I'm going to start with the cis portion first. So I'm going to make my tent. It could be on wedges or dashes. And I'm just going to draw everything that's left. So also going to have one over here. I don't think I'm going to draw it like that. Give me just a second. I'm going to draw both of them first. You'll see why in just a moment. This one's a little tricky. Let's just say they're both just say the rings are where we're going to not write stereochemistry, and we're going to keep our stereochemistry. I'm not drawing the ring right. It's not a bromine ring, it's a carbon with 2 bromines. Just a minute to fix it. Carbon with 2 bromines on it. Perfect. So now I'm going to indicate my stereochemistry. So on the cis one, I am going to just do them both on wedges, just for the heck of it. And for my trans one, I'm going to do one on a wedge and one on a dash. Now I have to be careful to connect them with the right amount of carbons. So we have 1, 2. Perfect. Nope. We have 1 carbon in between, so I need to make this go 1 carbon out. Perfect. And now you can write and enantiomer, and that would flip the stereochemistry for this one. But we also need to be cognizant of the fact that the cyclopentene, I don't know why I'm saying cyclopentene. Now I'm just spouting out nonsense. I am tired. It is a Sunday. This ring, this propyl ring with the 2 bromines on it, could have been trans the opposite way, with the bromines still both cis with wedges. And I'm going to draw that out if that doesn't make sense in words, just to show you what I mean. And this is also another possible product. This one was really tricky. I thought she was very mean for giving this one to us. Hui, I don't know how you felt about this one, but I thought this one was very mean.
I feel like this exam was significantly harder than the practice ones. Because I'm looking at my
I
practice
thought
one
so,
right
too.
now, and mine is way easier.
I know. And the last question on this one, I think, did anyone in our class get it right?
I do not remember. I remember this exam was really hard though.
Yeah, this exam was very hard. So to illustrate what I just said, this side, what once was the original alkene, could have been trans like this, with the bromine, the other side, still being cis on both wedges. And this one, you could also do the enantiomer. So you end up with, instead of 2 products, you could possibly have 4 products out of this reaction. It's very mean, it's very disgusting, it takes a lot of thought to do it. All right, yes, this is the last one, and I'm going to hand it off to Hui for a bit. All right, we have Ki and acetone as our reactants, and we have a 2-bromine substrate. We have 2 leaving groups. And so if you remember from the reaction summaries, this reaction removes 2 bromines, but they have to be anti to one another before they can be removed. So what happens is, let's just twist our Newman projection. That's going to be easier than trying to redraw it. So I'm just going to twist the front carbon. I'm going to leave the back carbon where it is. We still have our bromine down here. We still have our ethyl group out here. CH2, CH3. And we still have that CH3 over here. And now I'm just going to twist the front carbon. So I always imagine like I'm twisting a knob until that bromine on the top, the front carbon, is 180 degrees away from my bromine on the bottom carbon. So now I just have to move the other substituents accordingly. So the hydrogen ends up over here, and then the CH2, CH3 ends up over here. And so now, essentially what happens is we remove both of those bromines anti. And I just kind of drew it like this. This isn't the 100% mechanism, but it gets the gist along. And so I'm actually just going to erase them very carefully from my Newman projection. And I think it's a lot easier to leave it in Newman projection form. You could, if you really want to, draw it out. What you'd end up with is a trans alkene. You can see the biggest substituents are trans from one another. They're opposite. And then you just need to write out the 2 other products, which are KBr and IBr. Each one gets a bromine. Okay, any questions on this one?
All right. Hold on, let me switch my stuff. All right. Hope you guys can see that.
Yep.
Okay. So I'm just gonna try to go through the reactions that aren't redundant, and then go through multiple choice. And I think we should call it a day. I think you guys are.
Yeah, I think that would be good.
Okay, so I'll just go this real quick. So this one is acid. Remember this one. The important thing about this one is it's reversible. So I would attack the hydrogen and add OH. And this one uses a carbocation intermediate, right? So we would put the OH here. So we can do like this, and then we could do any stereochemistry here. So this one you guys seen a lot. So okay, this one you've also seen a lot. But important thing is that this one is like the opposite of the other one that adds mark. So it's anti-mark cis. So when I say cis, I mean that the two things that I'm adding is the hydrogen. Here, I'll turn these into dashes. And then I'm adding the hydrogen and the oxygen or the OH. So when I mean cis is I'm not saying that these two are cis, right? Or I'm saying that this what I added, the OH and the H are cis. And it's the exact opposite of the ones that you've seen before, right? Where the OH is mark and it's trans. So it's the exact opposite. It's anti-mark and cis with the BH3 H2OH. Okay, this one is actually a little bit different. So remember this group is the OTOS group. It's a good leaving group. And we see here, right? We see a strong base / nucleophile. So that means it's going to be SN2 and then E2. So first we can just do the SN2 reaction. So that's just going to be the O, CH2, CH3. Bam, text this leaves. We're going to get that's our SN2 product. And then we have still to do the E2 product. So this is a secondary. So what we do is we would either attack this hydrogen, move this here, move this here. Here. This should be reviewed. So, but basically what happened is that if the leaving group is on this carbon, then that means we can make double bonds here or here. That's just reflected on the two products that I made. And then again, we have that floating Na here, and we have the OTOS. So OTOS is negative. So one of the side products is going to be Na-OTOS. This will be a side product. So this is more review. Okay, so this one, I feel like a lot of you guys might be stuck on this because you see this and you're like, okay, I don't remember seeing that reagent anywhere. It's actually going to be N this. So the thing is, like, if you forget a reagent, right? So you forgot the first reagent, or you forgot what it does. Okay, but okay, I know what the second one does. So the second one, remember, it adds two OH's cis from alkene. So if I know that this one adds two OH's cis from an alkene, well then obviously this first one would have to form a double bond somewhere. And if you don't remember this base, it's actually a really good base for E2. So for E2, remember, you have to have trans. So there's a hydrogen here, and there's no hydrogens on this carbon, right? Because there's two methyls, so there can't be hydrogen. So this is the only hydrogen that you can actually use for E2 mechanism. So what would happen is that E2, we would form a double bond there. So we form a double bond here, right, due to the E2 mechanism. And then using the second mechanism, we're just going to add two OHs cis.
That's a neat trick. I like your trick. The only caveat is when it doesn't work and the second step's a no reaction.
Yeah. But, I mean, most of the time, like, she very rarely,
Most of the time it works.
yeah, she very rarely, like, tricks you, like, but just be careful. But most of the time, like, if you, let's say you don't know what this one does, always just go to the next step. Okay, what does this step do? And then if you don't know what this step does, okay, what does this step do? And then you can kind of work backwards from there. Oh, and then obviously this is going to be plus enantiomer. Okay. This one, so H2, HBr. This one is going to be anti-mark, so it's going to be adding a Br here. Here. The way I like to do it is when I see peroxide, it's always going to do something weird. It always likes to do like anti-mark. So I think mark is like the default, and then if I see like a peroxide, usually that means anti-mark. Like in this one here, there's a peroxide, and then the anti-mark. That's the way I like to remember it. Okay, so now we know that it's anti-mark. Put the Br on this end here, and then now what do we have here? We have Na. That's going to be a strong base. So we're just going to use it to attack. Boom. Okay, so then here I would count carbons just to make sure, because if you're adding like a nucleophile like this, it's good to count carbons. So we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. See, I'm actually missing a carbon here. Boom. Okay. So 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 3, 1, 2, 3. Yep. Okay, and then this one's also, like, we've seen this one a lot. See LCO. And remember, for this reaction, the first step is always going to be you attack the you do the CL, right? You're gonna make that tent, and you're gonna get this this thingy. Boom. So no, this is just this. Then we're gonna have the tents. Okay. And then from this tent, either the H2O is gonna attack or the CL is gonna attack. And remember, either way, it's gonna be trans. So you're either gonna get this product or you're gonna get this product. Okay, and then also here you cannot put plus enantiomer, right? Because this methyl right here, it doesn't actually change. It needs to stay on a wedge. So if you put enantiomer plus enantiomer, that would mean you have to change this. You would be changing this into a dash, which is incorrect. So you would actually have to draw physically like these on wedges and this one on dash. And then same thing with here, you have to draw this one on a wedge, or dashes, and then this one on a wedge. So there would be 4 products here. Okay. And then this one is the same thing that Sam said, where you have to put them trans to each other. So if I were to rotate it here, boom, struck it out. Okay, so this mechanism gets rid of two BRs at once. So what you do is you just erase the BRs, and you would form a double bond here. And if you notice it's cis, so if you want, you can draw it out like this. But it's a lot easier just to leave it as this Newman projection. Okay, this one. Okay, so I'm just gonna draw this out really quick. Okay, this is that. I think you guys would know how to do that, so I don't really feel like I have to go over that. And then remember, when you see like a carbene intermediate like this, the important thing is that whatever stays, or whatever's trans in cis stays cis trans. So like when I add the triangle with the CLs coming off, right? What's gonna happen? We have to keep the stereochemistry. So just like these two groups down here are cis to each other, they also have to be cis over here. And then here I can put plus enantiomer. And if you're confused about what we were saying about the plus enantiomer, you can just draw it out. Like there's no shame in just drawing it out. But it's just a little shortcut that you can take if you're feeling confident. So these are the two products. Okay. Oh, and then this one actually have no reaction because OH is a bad leaving group. OH can only be used as a leaving group if you're in an acidic situation, because what that does is you would turn this OH into this, which is actually a good leaving group, like, right? Because you can leave and form H2O. But since we're not in acidic conditions, OH is a bad leaving group. Okay, this. I'm just gonna draw out the reactant. Okay, MCPBA. This is the thing that makes that epoxide, little oxygen triangle. And remember, the thing with the triangle reactions is that whatever cis stays cis, whatever trans stays trans. So what happens is this, boom, I'm gonna put these two groups down here on wedges. This top group over here is just gonna be this. Boom. And then plus an enantiomer. The trick is just to memorize like what triangle it makes, and then also just keep everything the way it is. Okay, this one has a lot of products, but
that one's just review
yeah.
over like SN1, E1. I'd actually go back and just do the naming section on that exam, because that one's like the classical naming section that she has. And then maybe I'll do like the like you're given the reagents and you're given the product. What's the substrate? How's that sound?
Yeah, and then I'll just do multiple choice after this too. Okay, so this one is just memorization. It's just DMSO. She's probably not going to include that again just because it was already on this exam. But you should know what DMSO looks like. Okay, and then for this one, remember, same stats as always. Find the longest carbon chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, it looks like I got two options. So I can either go this, or I can go like this. And remember, one of the rules is we're supposed to find the one with the most substituents. This way, we only have this one substituent. But if we go this way, I can get two substituents. So now we have to see which one has priority. So the double bond is going to have priority over any of these methyl substituents, right? So we have to put this on the lowest number. 1, 2, 3, 4, 5, 6. So it's going to be 3 on the 3 here. 1, 2, 3. So either way is both the same. So now we have to look at the other substituents. So we do 1, 2, 3, 6. We do double on 3, and this one's on 5. But if I go this way, 2, 3, we actually get a lower number. So this methyl is going to be on 2 instead of 5, I think it was before, and this one's going to be in 3 where it was 4 before. So this is the most optimal naming for this thing. So now we just put all the stuff together. So we have a methyl on 2, so 2-methyl. Ethyl on 3, so 3-ethyl. And then we have a hexene. And now we just put it together. We have 3-ethyl. Okay, 2-methyl. And then you can do double bond is on 3, right? So that's going to be 3-hexene. Hexene with the E. Okay, and then one last thing. When you see a double bond, we have to consider E or Z. Okay, so the way that I like to think of it is that Z equals same side. That means that if the two largest groups are on the same side, then that means it's Z. So if we look here, so the largest group is this one, so it's going to be here. And then versus these two groups, this bottom one is larger. And see how they're cis to each other, right? They're on the same side, is going to be Z. Okay, any questions on that? Okay. So now here, same thing. 1, 2, 3, 4. This is definitely a cyclopentene ring. So we have to find the lowest numbers. So 1, 2, 4, 5. Or I can go the other way. But first we have to consider here the double bonds. So whether I go this way or this way, it doesn't really matter because I think the double bonds are going to be on the same numbers regardless. So now we have to consider the methyl subs. So if I go from here, the number is going to be lower for this methyl than if I go this way. So I'm going to start from 1, 2, 3, 4, 5. And the reason why I started from here instead of up here is because the double bond has priority. So I want to put the double bond on 1 rather than putting it on 2. Because the double bonds have priority over the methyl substituents. So now we just put it together. So we have 2, 5, 5, trimethyl. And then cyclopenta. 1, 3, diene. Or you can do 1, 3, cyclopenta, diene. Either one works.
Would you go back to 3H really quick in the reactions? You had a question on the orientation.
So how I got this or this?
I think the end orientation.
Okay, so if you're looking here, these two groups are cis.
Never mind. You said the beginning. Yeah, so you're right.
Okay, so this is just naming. So pentene, so that's going to be 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so 3-methyl. I'll just put it here. 1, 2. Yeah, 3-methyl. And 2-pentene. So that means the 2 is going to be here. Okay, so it says Z. So that means that the two biggest groups have to be on the same side. So here would be the biggest group. So I'm going to just highlight that in a different color. Be this one, right? And then over here, we're either looking at methyl versus a hydrogen. So the methyl is a bigger group. So that means I have to, in order for it to be Z, it has to be same side, right? So I'm going to put it up here. The same side. And then let me go to, yeah. So it looks a little weird because it's kind of upside down. So this and this would be here. So if I were to draw it like this, it's a little hard to see, but these two are the same thing because these two groups are cis to each other, two biggest groups. Okay, and then let's do some multiple choice. This is review, but this also, for some reason on this test, this section is really scuffed, so I'll just skip that. Okay. Which of the following, this is also review, but if you forgot, SN2, remember it has the rate law is going to be, oops, I had it pulled out. Whatever. It depends on both the substrate and nucleophile base. Substrate and nucleophile. So the rate law equation is this, right? Rate equals K times substrate times nucleophile. And then SN2, the reason why it's called SN2 is because it has two boxes here that determine the rate. That's just going to be U. Okay, so ranking alkenes in terms of decreasing stability. So more, yeah, okay. So we have to look for the most stable ones. So what I'm going to do is I'm going to just draw them out. So E3 heptene. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, 2, 3. And we put. Okay, and this is E because it's on opposite sides, right? It's E. Okay, 3,3 dimethylpentene. 1, 2, 3, 3, 3, 1, 2, 3. 3 dimethylpentene. What?
It's
Pentene?
just going to be on the end. The pentene is going to be on 1 because you
Oh
don't
yeah,
have to
yeah,
put
you
the
have
1.
to, you have to. That's the only way. Yeah.
Yeah.
Okay, Z. 1, 2, 3, 4, 5, 6. 3 methyl 1, 2, 3. 2 hexene here. And it says Z, so that means Zamzide. So that means I have to put this one up here. Remember, same side, boom, Z. Okay, and then Z3 heptene. 2, 3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 2, 3. Okay. This is Z, so Zamzide, we're gonna have to move this up. So 2, 3, so 2, 3. Then we're just gonna erase this other one. Okay, so time to rank these. So the most stable first. So the most stable is going to be. So just B is the answer. Okay, so let's reason through this. There's a third one, 2, 3. This one is the most stable because it has, first of all, it has 3 groups coming off of the double bond. So the more groups coming off of the double bond, the more stable it's going to be. So this one has 3, this one has 2, this one only has 1, and this one has 2. So first off, it's going to be this one. Number 1, because it has more groups coming off. It's the double bond. Okay. Second one is E3 heptene, which is this one. The reason why E is more stable than this one, right, is because trans is more stable than cis for this double bond. This has more steric hindrance, right, because they're kind of next to each other. These two groups are far apart, so that means that this one is going to be number 2, and this one will be number 3. Because remember, they both have 2 groups coming off of them, so they're pretty stable, but not as stable as this one, which has 3 groups. So first you're going to go off the groups, and then you're going to go off cis or trans. This one, remember, it has only 1 group coming off of it, so it's pretty unstable, and that's why it's 4th. Okay, so these types of reactions look a little difficult, but what I like to do is I like to draw the number. I just draw the carbocation and then just draw lines. Okay, so what happens is this will be carbocation like this here. Okay, and remember, also don't forget rearrangements. So if I hydride shifted, then there's another option would be this. Okay, here too. But also I can methyl shift. This would be another option. Same thing here. Okay, and the last one. This one actually has multiple. So I could Hydra Shift. Right, I could Hydra Shift here. Or I can also Hydra Shift down. I can Hydra Shift here. Okay, so which one has the most alkenes? So what I like to do is, let me get a different color. Like every time there's a carbocation, I just like to draw like lines. So this is a double bond, this is a double bond. Here too, boom, boom, boom. Just draw lines coming out from each positive. Okay, and the thing is like some of these might be overlapping. So you see how this one and this one would yield the same product. So that's what you just have to keep into account. So 1, 2, this one's already repeated, 3, 4. So this one has 4. 1, 2, and since this one did a methyl shift, these products are different. Oh, and also, you remember taking into account E or Z because this one's pointing down, but it could also be pointing upwards. So that's also another product that you can make. So this would be 1, 2, 3, 4, 5, and then 6. So 1, 2, 1, 2, 3, 4, 5. This one can go up. So 1, 2, 3, 4, 5, 6. This one, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. This one gives 8. So D is the answer.
Yeah, you did it the correct way. You did it the long way around. I think I just stared at it. I saw 3 carbocation intermediates. I said, that one's probably going to have more. And I moved on with my life.
Yeah, like this one takes a long time.
Yeah.
What else?
When you're
Okay.
done with multiple choice, you have a request to explain 3B and 3B's steps and the 3G final product. But I'll remind you of that. Just finish up multiple choice first, I'd say.
Okay, yeah. So most possible products. So this one is okay. So if I look here, this one it only makes the cis product. This one also only makes cis product. This one makes trans product. This one makes issue. This one does anti-mark, right? Let me just draw this out. Cyclopentene into dimethyl. Oh, okay. So the answer is this. You show it to HBR. Oh, okay, I see. It's because this one is not stereo specific. Wait.
I'm not sure if this one has the correct answer.
Wait, HBR.
Well, yeah, it does, because A only makes one product, and yeah,
Um,
B is not stereo specific, so yeah, you get multiple.
Yeah, I'm looking at B versus D, but let me just make sure.
It's because there are two methyl groups, one on each side of the alkene.
Oh yeah. This one's not stereo specific.
Stereochemistry, no, yeah.
Yeah. Yeah. So basically, so B would add. You could either have this, it would be like BR here, or BR here, or. So it'd be either this or this, and then it would also be like a star. So that would make like 4 products. And then these two only make 1 product, and then CL it would only make 2 products. Because it would be boom boom CL, but they would be trans. So one of them would be dash. Which, okay, you get the picture, whatever. Okay, so remember what Sam said about Hoffman or Zaitsev. This one's more subbed, this one's less subbed. So E2 reaction, remember, I feel like you guys always forget that E2, you need to be trans. So this one, I have one option here. You have one option here. This one option here. No options here. One option here, no option here. One option here, no options here. Okay, so only this one has 2 options. So one of the options would be to put it here, and the other one would be here, right? This is the only one with options at all. So that's the answer. Because the other 2, you can only make 1 product. You only can make 1 E2 product, right? Because I already said that you can't use here because it's not trans. Can't use here because it's not trans. Can't use here because there's no hydrogen. So this is the only one you can get 2 products, and if you want a Hoffman inside it, this is the one you have to use.
The Hoffman one comes off the methyl group that's on the same carbon as the bromine, just to specify. Yeah.
Yeah, whoops. Should be this into this. Yeah. Because you could technically do one here, but here is more Hoffman because it only has 2 stuff coming off. It has less stuff coming off of it. Yeah. Okay. What do I go over again?
The steps for 3B as well as the final product for 3G.
3B, 3G. The steps for 3B.
Yes.
This one there's no mech, I think, right?
Yeah, you wouldn't really need steps for this one. I guess you can just talk through it. This one's just more one that I've memorized.
Yeah, this one you just memorized. So basically, it's like the opposite of the one where you add OH mark and trans. You add this one cis. So the OH and the H are added cis. There's no mech for this one. They had a question on the mech.
And then 3G would be the other one.
Oh, this one? Okay. So remember what Sam said. So for this one, if there's 2 BRs in the KI, what it does is it removes both BRs at once just to create 1 double bond. So what you have to do is you have to make sure the BRs are trans. That's the only way this one works. So I'm gonna rotate the BR. I'm gonna rotate this back one, not this front one, but the back one to where the BRs are on top of each other. Okay, bam. They're trans. What I did was, right, I just moved this. So this BR is now down here. This H is now on the side. And this CH2, CH3 group is on this side. So what happens is you just simply erase the BRs. Because what you're doing is KI is attacking the BR, forming the double bond here, and then this BR is leaving. So what happens is this BR will be taken off. Okay, this BR is off, and there's a double bond here. And then I guess they're having issues of like how to draw this out, but you don't need to. But see how the double bonds here, so these two be cis to each other, right? So I'm just simply going to draw that. So double bonds, and these two are cis, so CH3, CH2, CH3. Draw this there. And the two hydrogens would be cis, right? So they would be here.
Perfect. All right, I'm going to take over. Make sure I get the right window. Okay. All right. I think that out of all the other sections on this exam, the last problem, I highly doubt you're going to see anything like this. This is the problem that I think everybody got wrong in our class. And then pretty much the other stuff is what was covered by Hui in the naming, etc. But this one can be a little bit tricky because you're kind of working backwards. So this one, it's really important to know what the mechanism, like what the reaction does and like what kind of substrate you start off with. So I see XSO3 and SCH3, two of them. So I know that this is going to be ozonolysis. So I know that this is some kind of cleavage reaction. And I know it could either be from an alkene or an alkyne. It can cleave both of them. So now I'm just going to go and take stock. I know that when I cleave an alkene, depending on the substituents that I have, like if I have two R group substituents on one side versus only one R group substituent on the other side, I know that I'm going to end up with a ketone and an aldehyde. So the aldehyde is going to come from the side with only one substituent, and the ketone is going to come from the side with two. So now if I think about what happens if I have an alkyne that I cleave, let's just say it has an R group on one side, and for the sake of it, I'm going to say that on the other side. Okay. When it cleaves, it makes a carboxylic acid on one side, and let me see if I think about it. It should also make formaldehyde on the other side. I think it makes a carboxylic acid, or it keeps oxidizing to CO2. I think it, keeps oxidizing to CO2. Okay. So now let's take stock of everything that we have in our product. So I see a COOH. So I have at least one carboxylic acid. I see another carboxylic acid up here. I also see that I have a single aldehyde and a single ketone. So let me just write out everything that I have. So I have one aldehyde, one ketone, and I have two carb acids. So H. Okay. Well, I know there wasn't a way for me to get a carboxylic acid out of alkene cleavage, but I could get an aldehyde and a ketone, which I couldn't get out of alkyne cleavage. So I know that these two came from the same alkene that was cleaved. And these two carboxylic acids, since I couldn't get them from aldehyde, or not aldehyde, alkene cleavage must have come from alkyne cleavage. So now it's just a matter of connecting the dots. So let's go to our alkene first. So this was one of the carbons that was part of the alkene. This was another one of the carbons that was part of the alkene. So what I like to do is, I imagine this double bond that's now connected to the oxygen is my alkene sticking out. So I need to connect it here to here. If I go to my two carboxylic acids, I know that this carbon was once part of the alkyne, and this carbon was once part of the alkyne. So I need to connect them here and here. So let me just draw out the base structure. So since we have a ring that's been broken, we know it's a ring because they're both on the same structure. They didn't form two different molecules for the alkene cleavage. I'm actually just going to number. It doesn't matter if it's correct nomenclature-wise. This is just for putting everything in the right spot. So let's see. 1, 2. Let me get rid of this. 1, 2, 3, 4, 5. So I know I start at cyclohexane. pentene. I'm going to renumber this just for the heck of it. I think I might be confusing myself. 1, 2, 3, 4, 5. So there are 5 carbons in the ring. I'm just going to go ahead and start off with my cyclopentene ring. I'm going to go ahead and number all the carbons that I have in my ring. Again, it doesn't have to be nomenclaturally correct. But so now I know that I've connected carbons 1 and 5. So I can very easily, I'm going to draw this in red just to show. I can very easily just add an alkene there. And now I'm going to add the other substituents, including that other alkyne. So I also know that off of carbon number 1, I have a methyl group that's here. I'm going to stick that methyl group on. And off of carbon number 4, I have an ethyl group. I'm going to go to carbon number 4, add an ethyl group. And then on carbon 3, which contains my carbon that was once an alkyne, I'm going to go ahead and stick my wedge on there. And so here I need to be kind of careful with my carbons. So I know I've got 1 carbon, 2 carbon, 3 carbon, and 4 carbon once I've added that alkyne back together again. So 1, 2, remember an alkyne is always going to be linear. So 3, 4, or 1, 2, 3. That doesn't look like an alkyne. There we go. And then the last one, which is still linear, 4. I know I kind of ran out of room here. I'm going to redraw it just a little better. Perfect. So now I'm just going to count my carbons, make sure I didn't miss anything. And let me just draw this in green, just to show you that this is where the cleavage occurred. All right, now to count carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 carbons in the product, 12 carbons in the reactant. Perfect. Any questions on this one? This one could be a little tricky if you forgot that it can cleave both alkenes and alkynes and make different products out of them. So that's how it can very easily be missed, like if you only did, like say the alkene, but you forgot the alkyne product. Okay, on to this one. So we know that these are the reactants to make this cyclopropane ring off of an alkene. So really, the very easy way to look at this is to just draw the alkene where you know it was in the product. You know that it added it on the alkene and it preserved the stereochemistry. So we know that this is a Z alkene. The 2 main groups, the 2 biggest groups, are cis to one another. So just to redraw that, and you could draw it sometimes with wedges and dashes just to show that you've preserved stereochemistry. I'm just going to draw it in Z conformation. So the 2 biggest groups are cis. I like Hui's little moniker. They're on the same side. And then that lone methyl group is on the opposite side. So that one's very simple. You could just look at the product, especially if you know what the reactant does, and just stick the alkene back on there. Okay, man, she really liked cleavage on this one. So here's another cleavage problem. So first I'm going to take stock of exactly the products that I could have from cleavage. So I have a ketone, I have 1 carboxylic acid, 2 carboxylic acid, and also a CO2. Now KMNO4 at acidic pH will make carbon dioxide from a terminal alkene or alkyne. So that's not very much help. So let's go ahead. We have 1 ketone. We have 2 carboxylic acids and 1 carbon dioxide. Now we can't get a, okay, wait. Just making sure I do this all right in case perfect. All right. So there are multiple ways that you could do this one, but you know that from a ketone and from a carboxylic acid, you can do from one of your carboxylic acids, you can make an alkene cleavage. And from another one of those not ketones, carboxylic acids and your carbon dioxide, you could very easily cleave a terminal alkyne. And so this kind of depends on how you Humpty Dumpty this back together again. So let's say, and it's just a little bit of a trial and error thing. Let's say I want to make a ring reformation. Could very easily do the ring here. So I'm just going to number it 1, 2, 3, 4, and then 5. So I know I've started with a cyclopentene ring. How do I know that one's the alkene? Because it has a ketone in it. We can't get ketones from cleavage of alkynes. 1, 2, 3, 4, 5. And from 1 and 5, we've got our alkene. Okay, let's draw in the other groups. 1, we have a methyl group. So let's put that on 1. On 4, we have a carbon that comes out, and that's going to be our other part where we have cleavage. So if we put these together, a COOH and a CO2, we end up with a terminal alkyne. Let's just say we did this another way. So I'm going to erase this work here. Well, what if we said, well, I don't know why my eraser's not working. There we go. What if we said, well, let's put these two together, and you'd end up with pretty much the same product. You could do this either way. Only thing, I'm not sure. Hui, if you look at the key, does it accept putting the 2 carboxylic acids together?
I don't have the 2023 key.
Oh, no, you can't do that. You can't put the 2 together because then you'd end up with an alkyne in a ring, and that would not be possible. So that's why you can't put the 2 carboxylic acids together. You're not going to see a ring, especially not a 1, 2, 3, a 3-carbon ring that has an alkyne in it. And that's the only way to get 2 carboxylic acids, really. Okay, any questions on that? I'm going to take a quick look at the key to make sure I haven't led you astray. But is there any questions? Yeah. Okay, and you could also have done it as both alkenes. I see it as an alkyne, but you also could have done, let me just draw it out. Gotta make sure I get back to the right window. Could also have done it like this. Okay. Oh, no, I think I drew that in the wrong place. And now I'm just drawing everything out of whack. Perfect. You also could get this product if you put these 2 together as a terminal alkene. Terminal alkene. And then these 2 together as an internal alkene. So there are multiple ways you could do this. I see the alkyne and alkene product, but you could do an internal and a terminal alkene. And that was all I was going to do. This one is really angry and mean. I highly doubt you're going to see anything like that. But if you want to go look at it, it is on the key. And pretty much the stuff up here is mostly just making sure that you know the terminology. So like tertiary, and you understand like what functional groups will occur with oxidative cleavage, what stability. So E is going to be more stable than Z, and you know geminal versus vinyl. And yeah, it's mostly just terminology that she's expecting. And this is pretty much kind of what we went through with the multiple choice. Hui, I don't know if you have anything you wanted to add from this section, since you took this test as well.
Here's Markov. I just hope that you guys don't get this test, like something similar, because this one is way harder than the other ones.
Yeah, and maybe I will talk about this one down here. So if we look at this last one on 1B, we can see with these sodiums all being here that we have all 3 carb anions on this carbon here. So I'm going to draw the negative, negative, negative. And if we remember the carb anion stability rules, they are most stable on an sp carbon. They are slightly less stable on an sp2 carbon, and they're the least stable on an sp3 carbon. So pretty much the opposite stability rules of your carbocation. So if we look at the hybridization state of each one, this one on a triple bond is on an sp. This one on a double bond attached to one hydrogen is on an sp2 carbon, a trigonal planar. And then this one is sp3. And so that's how you can very easily determine the ranking 1, 2, and 3, the sp3 carbon being the least stable. I would say this one, we did a multiple choice like this, ranking alkene stability, and then this one's just making sure you know the terminology, which ones will give you an anti-Markovnikov product. And very obviously, this one is specific for anti-Mark. This one gives you Markovnikov. And then this one's a base. It's very rarely, it could act as a nucleophile, but even so, it's pretty obvious. This is number 1. This is pretty obviously number 2. Regardless, that leaves this one as number 3 in last place. That's pretty much all that I'd say we have for you. Do you want us to post the worked on tests that we did? I don't know how much benefit it would be. Her answer keys are a lot neater than our scribbles. But if you guys want that, okay. So Hui will send out his and I'll send out mine. You're gonna do great regardless if your test's tomorrow or the next day. Study hard. I know that organic tests can seem daunting. They very much are daunting, but you've got this. If you know the reactions